for your introduction. Welcome everyone. Let me go straight to the presentation outline to actually indicate what I want to talk about today. As an introduction and background, I will talk about what actually nano-fretting is and motivation for nano-fretting experiments. After that, I'll explain the experimental setup that we used in the 3 case studies that I will introduce afterwards. These case studies are on nanomechanical testing of silicon, nano-fretting of carbon films, and nano-fretting of biomaterials. And finally, I'll summarize my my talk. Okay, so what actually nano-fretting is? Let me start with general fretting definition first. Fretting is a specific surface damage process of nominally stationary joints which progress through micro-displacement oscillatory motion, and it's typically in the range of few microns to few tens of microns. Depending on the loading conditions, we can distinguish between fretting fatigue and fretting wear regimes. Fretting fatigue is observed under high contact pressures and smaller displacement amplitudes, and the resulting surface damage is crack nucleation and propagation. Fretting wear, on the other hand, results from larger displacement amplitudes where full sliding is observed at the interface. And in that case, surface damage is through debris generation and loss of volume. On the right-hand side, here I listed a couple of typical applications where fretting has been observed, including suspension bridge ropes, electrical connectors, turbine blind joints, screw joints, or medical implants. So the scope of this work and case studies presented in this talk today is fretting wear, which typically progresses through 3 distinctive stages for most of the materials. So in stage 1, the interface is cleaned by rubbing from contamination and oxide layers, and what is called tribologically transformed structure is formed, TTS structure. So in the second stage, the TTS structure is being fragmented and wear debris are generated. Finally, in stage 3, the tribological system reaches some sort of steady-state equilibrium between new debris generation and the interface debris ejection from the contact area. And this mechanism is valid for classical macro-fretting situations and nano-fretting experiments. This is the first time nano-fretting is actually mentioned in this talk, and it has to be pointed that there actually is no nano-fretting definition established in the literature. Many researchers, including myself and my colleagues, refer to small-scale fretting experiments as a nano-fretting, really to indicate the reduced scale of the method. And what I actually tried to do on this slide is to form a nano-fretting definition based on geometrical parameters of tribological contact. So what we see here is the first condition of that definition, and it's based on E coefficient proposed originally by Siegfried and co-authors, and in compares the Hertzian contact area with sliding amplitudes measured at the interface during fretting. And here we simply deal with the fretting situation if the ratio of a sliding amplitude and Hertzian contact radius is smaller than 1. And when there is an exposed surface area maintained within the wear scar, which is shown here. Any situation with larger displacement amplitude is considered as a reciprocating sliding. So that was the first condition of the nano-fretting definition. The second relates to the third dimension of the wear scar, namely wear depth. it simply links to the general nanotechnology definition, stating that it is the branch of technology that deals with dimensions and tolerances of less than 100 nanometers. So with those two conditions, we can actually arrive at the nanofretting definition and say that it is a specific surface damage process resulting from a small displacement amplitude oscillatory motion between two nominally stationary solid bodies in contact under a normal load, with the unexposed surface maintained at the center of the fretted surface, resulting in wear depth of less than 100 nanometers. Okay, so that brings me to the second short part of my talk on why nanofretting or small-scale fretting experiments are relevant. I like recalling that particular figure and similar Moore's law type of data, showing that we are really living in a time of exponential growth in all areas of technology. What we have here is time on x-axis and diameter of mechanical devices on y-axis. This particular figure shows decrease in size of mechanical devices over the last 40 years. And clearly the tribological challenges we are facing, we were facing in the 80s, are very different in terms of contact size and loads involved to the problems we face today. So in general, miniaturization of mechanical devices results in severe contact conditions generated by relatively small forces. As we know, performance of materials at small contact scales is a significant challenge, and tribology becomes really an enabling technology for any small-scale devices with moving components, including, of course, MEMS devices. So silicon-based MEMS devices and technology has reached nowadays really sufficiently mature level to be able to provide some commercial applications. However, highly complex mechanical and tribological behaviors of silicon remain still a main challenge. So in that respect, also fretting experiments performed at small contact scales bring specific challenges, and that will include for fretting increased importance of surface energy and adhesion, role of wear particles, and impact of surface roughness. The novel macro and nanoscale mechanical testing methods, including small-scale fretting experiments, have also an important role of filling so-called the measurement gap, which has been identified between conventional tribometers and AFM techniques as defined here in this figure introduced by Dress and co-authors. So this type of small-scale mechanical testing methods will play a key role in miniaturization of mechanical devices, and we will probably see more and more of that type of testing coming over years. Okay, so let me now introduce the experimental setup that we used in the case studies. So we used the third generation of the NanoTest Platform located in School of Mechanical Engineering at the University of Leeds, and most of the results shown today relate to reciprocating nanofretting type of experiment. However, for some nano-indentation and nano-scratch data will be also presented today for comparison. So these are the three out of 5 modes that we can reproduce on Nano test platform that we will be focusing on today. NanoTest Platform operates on a well-established pendulum design controlled by the coil and the electromagnet in the top part of the pendulum. And for nanoware and nano-fretting experiments, a special module is attached in front of the indenter, responsible for inducing the reciprocating movement of the sample. So this module, the fretting module, can be seen on the picture here with sample attached and positioned in the front of the indenter. On the right hand side here we see a schematic diagram of the fretting module. So this is the area where we attach the samples. Here we see a piezo stack generating reciprocating motion, which is then magnified through this ceramic arm, rocker arm, and delivered to the samples. Using different probes and geometry, which are shown here as an example, we can generate certain required contact pressures, and typically we would be using diamond probes for this kind of experiments. Okay, so that brings me to the first case study, where we looked at comparison of nano-indentation, nano-scratch, and nano-fretting of silicon using the same spherical probe. The rationale for that work was really lack of full understanding of mechanical behavior of silicon under more complex kinetic conditions that can occur in practical tribological situations. So this table summarizes the test conditions used in the study with the range of peak loads indicated here for nano-indentation, nano-scratch, and nano-fretting experiments, loading rates that we use for the experiments, scan speeds for dynamic testing for nano-scratch and nano-fretting, and other conditions like track length for nano-scratch, nano-fretting, and hold at peak loads for nano-indentation and nano-fretting. So these are the images showing individual indents between 50 and 500 millinewtons load with some cracking and then delamination visible under higher loads. And these are corresponding loading curves which we can analyze, and we can try to identify some critical loads, which is done here, and by comparing optical images with recorded data, we can identify some first silicon popping events at around 40 millinewtons, cracking around the indentation site at around 200 millinewtons, and some radial lateral crack system developing above 300 millinewtons. And we will use that data, this critical events data, for comparison of some critical loads in nano-indentation, nano-scratch, and nano-fretting later. This is just a nice image of indentation site at 450 millinewtons, showing extensive cracking and delamination. So going to nano-scratch data now, what we can see here is a typical scratch track with the on-load scratch depth data, optical image above of the scratch, and the residual depth signal. All this was used to assign the nano-scratch critical loads, and the main transitions are listed on the right-hand side with onset of non-elastic deformation, popping events, chipping, and lateral cracking. Again, we will use that data for comparison with nano-fretting later. So finally, to nano-fretting data, this is fretting scar wear volume measured by 3D laser microscope as a function of applied load. So red dots are representing tests without fretting oscillation engaged, and blue dots correspond to actual fretting tests. So what we can see here is a clear increase of wear volume under fretting conditions comparing to the static experiments. We can also see that with increasing load, damage becomes more progressively greater at around 110 millinewtons, and transition to more severe damage mode observed here with tests at 100 millinewtons, showing really more stochastic behavior. So the three circles here indicate the wear scars captured on SEM images, which are here. So this is a fretting wear scar under 90 millinewtons load after 1000 seconds test. We see some agglomeration of wear debris, and measured wear volume in that case is 2.1 cubic micron. Same test conditions here, apart from the applied load. In that case, load was increased to 110 millinewtons, resulting in clearly deeper wear scar and almost 50 microns wear volume. Finally, third image showing wear scar under 200 millinewtons load. So some excessive silicon damage observed here, lots of cracking, lots of debris, and order of magnitude really larger than in the previous case at 416 cubic microns. And if we compare that image with a classical macro-scale fretting scar shown here, we can really see the similarity of the wear scar morphology, although the scale is very different. So that's an interesting comparison. So this figure shows a comparison of typical load versus displacement loading curves for nano-indentation, nano-scratch, and nano-fretting. It's a bit busy figure, but for the nano-fretting test, the depth and the center of the 2-micron tract is shown here. And for the nano-scratch, the load varies linearly with position. So each load depth point here corresponds to a different point along the scratch track on the silicon surface. So the behavior at the load is clearly very similar, with differences becoming more significant and dynamic as the load increases. So critical loads observed for three types of experiments are summarized in this table. After correction of the scratch and fretting data for instrument rate compliance, the different types of tests can be actually more directly compared. And as we observed from the loading curves on the previous slide, the deformation observed in the three types of contact shows some similarities but also notable differences as the applied load increased. We can see that silicon phase transformations induced in the nano-scratch and nano-fretting tests are more complex, and tangential loading promotes yield, resulting in greater penetration depths than in nano-indentation. So that brings me to the second case study, which is actually a collection of data from various tests on carbon films. Let me start with the basic indentation data first. This figure shows typical nano-indentation curve for 100 millinewton load on 80 nanometers film and uncoated silicon as well. At low load, the curves are elastic and visually identical, as both are due to elastic behavior of the silicon, of the substrate. As the load increases, small but clear differences are observed, and with some pop-ins on silicon at around 37 millinewtons, at around 43 millinewtons on the carbon film, an additional popping at higher load, more obviously on the TEC film at around 76 millinewtons. The pop-out during unloading occurs at higher load on the uncoated silicon. So this data show that mechanical response of a coated system is slightly modified by the coating. However, it is still heavily influenced by the mechanical behavior of silicon substrate. So when it comes to fretting, we analyzed surface damage with SEM images, revealing fretting scar and wear debris morphologies. However, more specifically, we were interested in EDX analysis here. And EDX line profiles taken here across the fretting wear scar allowed us to measure gradual wearing of the films. This is the EDX spectrum of 1500 cycle test, which reveals really thinning of the film and oxygen incorporation in the worn region. What is interesting is that there was no abrupt changes in depth or friction observed in case of these films, which could indicate some sort of surface failure. And we observed this type of abrupt changes in depth signal previously on other carbon-based film, as shown on this figure here. However, to induce film failure rapidly at low load, a sharper pyramidal Berkovich test probe was used here. The changes in probe depth after 240 and 320 are actually in good agreement with some multiple failure events observed in nano-scratch tests performed earlier in the studies. Now I have a couple of slides left on DLC coatings under nanofretting before I finish with this case study. So three types of DLC coatings with various thickness and roughness, as shown in the table here, were studied. Through nano-indentation, we measured hardness and elastic modulus of all three coatings, but more importantly, we were interested in H/E ratio, which is shown in more details here. It has been shown in the literature that there is a link between H/E ratio of the materials and their tribological performance. So we really wanted to correlate that parameter here with DLC coatings nanofretting performance. So this figure shows H/E ratio for all three coatings as a function of indentation contact depth, with coating A having the highest ratio value. This is a typical result showing fretting behavior of DLC coating A with evolution of wear depth in black as a function of force, and friction force in gray as a function of fretting cycles. The test conditions used are listed here. We used 5 micron diamond probe, 100 millinewtons applied load, track length was around 13 microns, and frequency of 5 Hz. And the inset here shows a loading history to 100 millinewtons peak load with 900 seconds fretting time. And this is a summary of nanofretting wear depth for 3 DLC coatings tested, really indicating clear ranking of the coatings, with coating A experiencing significantly less wear than other 2 coatings. Also, this ranking corresponds well to the H/E ratios established earlier, where coating A had the highest H/E coefficient. So finally, case study number 3 on nanofretting of biomaterials. And the aim of this study was to gain greater understanding of the onset of wear for improved design of biomedical devices through improved nanomechanical testing. So we used 3.7 micron spherical diamond probe. Loads applied in that case were in the range from 1 to 30 millinewtons, 10 microns track length and 10 Hz frequency. And the test samples used were highly polished medical grade cobalt chrome alloy, 316L stainless steel and titanium alloy. I will jump straight to nanofretting results here, and the two figures show load dependence through 30 individual nanofretting experiments on each material as a penetration depth. In the first case at the end of 10 seconds loading ramp, and in the second case at the end of 290 seconds peak load. For all applied forces between 1 and 30 millinewtons. In both cases, cobalt chrome alloy shows the highest resistance to fretting wear. In the same time, it is quite difficult to distinguish between wear behavior of titanium alloy and stainless steel. However, stainless steel seems to perform slightly better at the end of the peak load. The difference is probably more clearly visible here under the constant load test under 30 millinewtons, where initially stainless steel performs better than the titanium alloy. However, with repeat wear cycles, its performance deteriorates more rapidly. And cobalt chrome alloy still shows the highest resistance to nanofretting here. The probe depth measurements obtained directly from the fretting experiments indicating the extent of wear can be compared here with the scar morphologies revealed on SEM images. So again, the least wear amount is observed under increasing load from 2 to 30 millinewtons for cobalt chrome alloy. And please note the different scale for 30 millinewtons case. So we have 5 microns here and 10 microns here. And the images allow also for further wear mode and wear debris morphology analysis for really better understanding and improved design of biomedical devices. And that brings me to the summary of today's talk. So let me just read through the points here. So nanofretting is accelerated nanoware technique, proving to be a valuable testing tool, and it is complementary and extends the capability of nano-indentation and nano-scratch experiments. Dynamic tangential loading in nanofretting test promotes yield, resulting in greater penetration depth than in nano-indentation and nano-scratch. In the case studies presented today, the method has been used effectively to characterize the mechanical properties and the nanoscale tribological behavior of a series of materials, including anti-wear applications. In terms of future work, that will involve extended duration fatigue tests, tests in liquids, and development of modeling tools for better component lifetime predictions. And finally, more applications for this method are likely to emerge due to general miniaturization and increased energy densities of mechanical systems. So that's all from me, really, and now I'll hand over to Mike at Micromaterials for a panel discussion. Thank you very much for your attention.
Okay, thank you, Thomas, for that talk. Just get my screen up here. So, yes, when